The old picture of black holes, and Stephen Hawking believed this for a long time, had a bet about it actually, is that they seem like they destroy information. You can just kind of see it goes to the end of time, right? It's gone. And then they evaporate away, and it seemed that there was no way, even if you gathered all the Hawking radiation that had come off for trillions of years, there's no way you could reconstruct what went in. So therefore, if you jumped into a black hole, you'd be erased from the universe. But that breaks pretty much every law of physics, right? Things don't erase information. They scramble it up, make it difficult to read, but they don't destroy it.
Imagine you are floating through the blackness of space. There is no up or down, no breeze, and no sound. Stars twinkle at impossible distances. Suddenly, you feel a pull. It begins almost like a gentle tug on your limbs, then grows stronger. Your spaceship's controls strain as if caught in a hidden current. You glance at your instruments and see you are being drawn toward a dark circle that absorbs light itself. At first, your mind questions the reading. Instruments can fail, sensors can glitch. Yet every system registers the same fact. You are approaching a black hole. Your view of the galaxy behind you fades as if someone draped black cloth across your viewport. A strange stretch runs through your body, a pull that tugs at your feet more than your head. Time feels odd. Seconds seem to pass differently. You are witnessing space-time warp.
But now we think, actually, no, even black holes don't destroy information. So it turns out that now we think, and this is very 2022 papers, right? If you jumped into a black hole, then we do think that if a super being in the far future could collect every bit of Hawking radiation that came off the black hole for trillions and trillions of years and stick it into a giant quantum computer, then they could reconstruct everything that fell in. So actually, in some sense, you come out.
What is a black hole? In simple terms, it is a region of space where gravity is so strong that nothing can escape. Not dust, not gas, not light. It forms when enough mass is squeezed into a small volume. Imagine a star far more massive than our sun. Over millions of years, it burns its nuclear fuel. When that fuel runs out, there is no pressure left to hold up the star's own weight. The outer layers collapse inward. If the leftover core is heavy enough, more than about 3 times our sun's mass, it keeps collapsing until it shrinks to a point where gravity wins over all. Dr. Brian Cox explains it this way. Take a star with the sun's mass, then squeeze it down until its radius is just 3 kilometers. At that size, the escape velocity, the speed you need to break free, goes past the speed of light. Nothing travels faster than light, so light itself is trapped. He calls that boundary the event horizon. Once you cross it, there is no return. The size of that boundary is set by a simple equation from general relativity. It is directly proportional to the mass of the object and inversely proportional to the square of the speed of light. For our sun, that radius is only about 3 kilometers. For a black hole with 10 times the sun's mass, it is 30 kilometers. Though the mass grows linearly, the radius remains tiny by everyday standards.
Described by Einstein's theory of general relativity, they are distortions. In Einstein's theory, they're distortions in space-time. And their distortions are so extreme that there's a region from which light can't escape in this space-time. So the classic example is the collapse of a massive star, which essentially the history is that in 1916, so only just a few months after Einstein published his theory of general relativity, Carl Schwarzschild showed how space and time are distorted outside a perfectly spherical, non-spinning ball of matter. So it's a solution of Einstein's equations. So it tells you the distortion of space-time outside a star, a simple model of a star. Now, it turns out that in those equations, if you just keep the distortion but remove the star, but leave the mathematics there, then you have the description of a black hole. So it's in there. And actually, interestingly, if you allow this solution to go infinitely far into the past, and so you just have this, you kind of continue it into the past, you get a description that's not only a black hole, it's a wormhole with a black hole and two universes and a white hole and one bit. So it's all there in the mathematics from 1916. So they're very natural in that sense. The question becomes, as we said earlier, does nature create such things, given that it can exist? Can nature do it? And that was the debate, actually, into the 1930s.
At first, black holes were only a twist in Einstein's equations. In the 1910s and 1920s, physicists debated whether these singularities were real or just a sign that the math had broken. They thought perhaps nature would forbid matter from collapsing that far. But in 1964, Roger Penrose proved that once a star passes a certain point, collapse is inevitable. Since then, indirect signs of black holes have kept piling up. Astronomers first spotted strong hints in the 1960s and 70s. They saw X-ray sources flickering in our galaxy. Models showed that gas falling toward a compact object would heat up to millions of degrees, glowing in X-rays before disappearing over the horizon. They discovered Cygnus X1, the first strong black hole candidate, by watching a companion star wobble as if pulled by an unseen mass. In recent years, detection leapt forward with gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, caught ripples in space-time from two merging black holes. They were about 30 times the Sun's mass each, spiraling inward until they collided. The shock of that collision sent out waves that stretched and squeezed Earth by a fraction of an atom's width. It was our first direct measurement of black holes merging. Since then, LIGO and its partner Virgo have recorded dozens of mergers. These events reveal how common stellar mass black holes are, how they pair up, and how fast they spin. Each detection helps refine our understanding of star formation, supernova explosions, and the dynamic life of binary systems. Black holes come in three main families. The smallest are stellar mass black holes, weighing a few to tens of solar masses. They form when massive stars end their lives. Next, intermediate mass black holes, with hundreds to thousands of solar masses, hide in the hearts of dense star clusters. They are harder to find but may form when stellar black holes merge over time. The largest are supermassive black holes, millions to billions of solar masses, anchoring the centers of galaxies. Our own Milky Way hides one of those giants at its center. It is called Sagittarius Aar. It sits 26,000 light-years from Earth. It weighs about 4.3 million times the Sun. If you replace the Sun with it in our solar system, its horizon would reach out just inside Mercury's orbit, less than 1/5 of the distance to the Sun. Its mass is immense, but its size is small in cosmic terms. In April 2019, the Event Horizon Telescope gave us our first direct view of a black hole's shadow, if you can call it that, in the galaxy M87. What we saw was not the black hole itself, which emits no light, but the glowing ring of the accretion disk. That disk is made of gas and dust, spiraling inward, heated to extreme temperatures by friction and magnetic forces. It shines in radio waves, which our global array of telescopes captured. In our imaginary spaceship, we hover just outside that disk. The glowing ring curves around the black hole. We see the near side directly, but gravity bends light from the far side, making it appear above and below the horizon. Light from behind wraps all the way around and reaches our eyes. The result is a bright ring surrounding a dark circle. If we approach that boundary, we would feel no abrupt change. Inside our ship, we would float as if we were weightless, just like astronauts in orbit around Earth. Our autopilot would hold us on a steady course toward the hole. We might see particles of gas glowing outside, but once we pass the edge, no light shines back. To someone far away watching through a powerful telescope, our journey would look very different. They would see us slow down, inching closer to the circle, moving slower and slower. Our clocks would tick more slowly compared to theirs. They would freeze on the horizon, our image reddening until it fades away. That effect, called gravitational time dilation, happens because the powerful gravity near the hole stretches time itself. For us inside the ship, time runs normally. We cross the horizon in just a few seconds or minutes, depending on the hole's size. We don't feel an invisible wall. We do not see the dark circle expand or change. We just float past. But once inside, a new force grips us. Gravity at our feet pulls harder than at our heads. That difference grows as we fall deeper. Soon it beats on your feet like giant hands while your head feels less pull. You stretch into a long, thin shape. This is why physicists call it spaghettification. Dr. Cox describes the process. You start to feel this stretching and squashing. Space and time warp differently at each end of your body. That tidal force increases as you approach the singularity until, atom by atom, you pull apart. First your body, then your atoms, then even the particles inside atoms may split. What awaits at the center of a black hole is called a singularity. In Einstein's theory, it is a point where density goes to infinity and the laws break down. But it is better imagined as a single moment in time. Whatever you are, you move toward that moment. There is no space to avoid it. It is your future, and you cannot turn back. Quantum physics adds another twist. In 1974, Stephen Hawking showed that black holes are not perfectly black. Near the horizon, pairs of particles pop in and out of existence. One may fall in, the other escape. That escaping particle looks like heat, as if the hole glows at a temperature inversely proportional to its mass. Smaller black holes glow hotter and evaporate faster. Large ones like Sagittarius Aar glow at temperatures near absolute zero, far colder than space. Hawking radiation means black holes slowly lose mass over time. A stellar mass black hole might vanish over 10 to the power of 67 years. A supermassive one could last 10 to the 100 years or more. Those spans dwarf the current age of the universe, 1.4 times 10 to the 10th years. Hawking's result raises the information paradox. In quantum mechanics, information cannot be lost. If you toss a book into a hole, the data in its pages should survive somehow. But if the hole evaporates completely, where does that information go? For decades, physicists argued that information might vanish, breaking quantum rules. Then in 2019, a set of papers suggested a resolution. They show that Hawking radiation can carry information, but not in a simple way. The radiation must be entangled with the stuff inside. As evaporation proceeds, that entanglement changes, so information leaks out. Physicists use terms like page curve to describe how the radiation's entropy first grows then falls. One idea is that quantum effects create tiny connections, wormholes, between the inside and the radiation outside. Through those links, bits of information slip out. Another view comes from the holographic principle. It suggests that all the data inside could be encoded on the horizon's surface, much like a two-dimensional film stores a three-dimensional image. No single picture is agreed on yet. Some researchers propose firewalls, energetic sheets at the horizon that would fry any infalling object. Others argue for fuzzballs, where a string theory description replaces the hole with a tangled ball of strings and no empty interior. It is an active debate, and experiments are a long way off. Why study black holes so closely? They probe gravity under conditions we cannot create on Earth. They stretch our theories to their breaking points and force us to find a unified view of gravity and quantum mechanics. They also shape the cosmos. Supermassive black holes feed on gas and dust, launching jets that regulate star formation in galaxies. They help set the stage for the growth of structure in the universe. Black holes power quasars, the brightest objects we see across billions of light years. In their centers, infouling gas heats to extreme temperatures, shining more brightly than an entire galaxy in some cases. That light lets us trace the history of the universe back to when it was less than 1 billion years old. Looking ahead, new tools will sharpen our view. The next generation of gravitational wave detectors, such as LISA in space, will catch waves from pairs of massive black holes billions of light years away. The next version of the Event Horizon Telescope will add more telescopes and higher frequencies, giving clearer images of horizons and jets. We may map magnetic fields twisting around holes and watch matter swirl in real time. Could humans ever go on a mission into a black hole? In practical terms, no. The radiation near the hole would cook any spacecraft. The tidal forces would tear it apart. Once you cross the horizon, no signal could return, but in thought experiments we can send signals, probes, or even quantum particles to learn what happens inside, then decode the information in the Hawking radiation. That leads to a deeper question: is space and time itself made of something like quantum bits? Some theories suggest that space-time emerges from entanglement between tiny building blocks. In that view, studying black holes may reveal the quantum structure of space. We may learn that the universe is like a vast quantum computation where geometry and gravity arise from underlying information processing. Black holes blur the line between physics and information science. They force us to rethink how data, energy, and geometry interact. They hint that the ultimate theory of nature will weave together particles, forces, space, time, and information in a unified framework. Our journey into the heart of a black hole has shown us how gravity shapes space and time, how matter and light behave at extremes, and how quantum effects hint at deeper laws. But the story does not end at the singularity. In fact, black holes help us trace the life cycle of galaxies. When massive stars die, they feed smaller black holes. Those black holes merge over millions of years, growing larger. Their gravity pulls in gas and dust, driving the formation of new stars even as they light up the cores of galaxies. Black holes act like cosmic recyclers, breaking down old stars and helping forge new ones. In that way, they link endings and beginnings across the universe. In the coming decade, new observatories will deepen our view. On the ground, next-generation telescopes like the Extremely Large Telescope will resolve stars moving around our galaxy's center with finer detail. In space, LISA, the Laser Interferometer Space Antenna, will listen for low-frequency gravitational waves from mergers of supermassive black holes in distant galaxies. Meanwhile, upgrades to the Event Horizon Telescope will sharpen images of horizons, letting us watch gas swirl and jets form in real time. Each new data point helps us test general relativity, refine models of accretion, and chart the growth of black holes over cosmic history. On the theory side, researchers are building bridges between gravity and quantum mechanics. They use computer simulations to model how information might escape a black hole, guided by ideas from quantum information theory. In labs on Earth, physicists create analog systems, such as fluids flowing past sound horizons, that mimic aspects of black hole physics. These tabletop experiments let us probe effects like analog Hawking radiation, offering clues about how real black holes might behave at the smallest scales. That blend of observation, theory, and experiment drives progress. Beyond the science, black holes invite us to rethink our place in the universe. They show that time and space are not fixed backdrops, but dynamic elements that bend, stretch, and end in ways we still struggle to grasp. They remind us that our current theories, however successful, have limits. Each time we probe a black hole, we test the rules we hold most certain. In that trial by gravity, we refine our understanding and open the door to new ideas. Exploring a black hole is as much a journey of the mind as a voyage through space. If you feel inspired, you can join the effort. Follow public data releases from LIGO and Virgo, sign up for citizen science projects that classify galaxy images, or look for changing light in sky surveys. Watch the Event Horizon Telescope's next releases and read up on the latest papers in quantum gravity. Talk with friends about the strange fate that awaits anything crossing an event horizon. Share your questions, sketch diagrams of warped space-time, or simply gaze up at the night sky, knowing a hidden world of extreme physics lies beyond the stars. Black holes are no longer distant curiosities. They are keys to a deeper picture of reality. As we push forward, every new discovery brings fresh questions, but that is how science moves ahead, step by step, question by question. If you look up at the night sky tonight, find a dark patch between the constellations Sagittarius and Scorpius. That is where Sagittarius Aar lies. Invisible to our eyes, it anchors millions of stars as they whirl in close orbits. Its quiet presence hides a ceaseless struggle of gravity, motion, and time. In the words of Dr. Cox, black holes are places where space and time themselves are on display. They force us to face the raw structure of the universe. As you learn more, your sense of wonder can grow. The universe keeps its secrets well, but it also offers us the tools to uncover them. Our trip has taken us from the edge of the galaxy to the brink of all we know. We have seen how stars die, how gravity rules, and how quantum effects spark light from darkness. We have traced the path of falling matter, watched time slow, and faced the moment where space and time end. There are no easy answers at the Singularity, but that is where new ideas wait. There, our current theories break open, and a deeper picture may emerge. Until then, black holes remain laboratories for our imagination and our experiments. They challenge us to build better theories and better instruments. In the end, black holes are not just cosmic oddities, they are doorways. They connect gravity with quantum fields, stars with galaxies, and the very large with the very small. They remind us that science is a journey, and every advance opens new questions. So if you have ever wondered what it would feel like to fall into a black hole, now you know. You would float, then stretch, then vanish into a point that marks the end of your time. But your voyage would also bring you face to face with the deepest laws of nature. Whether our theories hold or need revision, black holes will guide us to the next frontier. And as always, keep looking up at the night sky. There is more to see than meets the eye, and every star you spot hides stories of gravity, light, and time. The universe has many more chapters to write, and black holes are among its most compelling. Let that sense of wonder carry you onward toward new horizons of discovery. So thanks for watching this video. If you enjoy watching it, give it a thumbs up and subscribe to our channel for more content.